boundaries of physics are being redrawn right before our eyes. Thanks to a remarkable advancement in generative AI, our understanding of the physical world is entering a new era. Highlighted in a recent MIT article, this innovative breakthrough introduces a generative AI technique capable of automatically classifying different phases of physical systems. This development is not just a step forward, it's a leap towards future technologies and materials that could transform our daily lives. In this video, we'll explore the mechanics behind this revolutionary tool, its profound impacts, and the broader implications for science and technology. Join us as we delve into how this AI is unlocking secrets of the universe that were once thought to be beyond our grasp. Generative AI is a branch of artificial intelligence that focuses on creating new data instances that resemble training data. It's like teaching a machine to mimic complex patterns, generate novel ideas, or predict new outcomes based on massive amounts of information. One popular example of generative AI is the use of generative adversarial networks, GANs, where two neural networks contest with each other to create increasingly accurate or realistic data. In the context of physics, generative AI does more than just generate data. It helps us understand and interpret complex physical systems in ways that were previously inconceivable. By learning from existing data about physical states and properties, these AI models can predict new states or transitions between states. This capability is especially useful in material science, where understanding phase transitions, like from a solid to a liquid or from a magnetic to a non-magnetic state, is crucial. The new technique discussed in the MIT article represents a significant advancement in this area. It utilizes a type of generative model designed to classify and predict phases of physical systems automatically. This model is trained on known data and then tasked with predicting unknown data, effectively learning the underlying physics that govern these transformations. This not only accelerates research and development by reducing reliance on slow and costly traditional methods, but also opens up possibilities for discovering new materials with desirable properties that could lead to technological innovations in various industries, from electronics to aerospace. The recently developed generative AI technique for classifying phases of physical systems is groundbreaking in its approach and functionality. This technique, which involves sophisticated algorithms, is built on a foundation of deep learning and pattern recognition. It has been designed to accurately identify and categorize the various phases through which a material can pass, such as different states of matter or magnetic properties. What sets this technique apart is its ability to handle vast amounts of data and its adaptability to different types of physical systems. The AI model learns from each dataset presented, improving its predictive capabilities over time. This is crucial in physics, where experimental data can be complex and voluminous. By training the model on known phase transitions and the conditions that cause them, the system can then predict unknown transitions, potentially discovering new phases that have not been observed experimentally. This capability is transformative. For instance, when exploring new materials for superconductors or semiconductors, scientists no longer need to solely rely on traditional, often tedious experimental methods. Instead, they can use this AI to simulate and predict material behaviors under various conditions much faster than traditional laboratory experiments would allow. This not only speeds up the research process, but also reduces the costs associated with material discovery and development. The technical sophistication of this tool lies in its neural network architecture and the training process, which includes unsupervised learning from unlabeled data. This is a significant advance because it reduces the dependency on extensive pre-existing annotated datasets. The AI's ability to learn and adapt to new data without human intervention makes it a powerful tool for advancing our understanding of the physical world. The implications of this generative AI technique extend far beyond the laboratories where they were developed, particularly in the field of material science. This area of study, which focuses on the discovery and design of new materials, stands to gain immensely from the capabilities of advanced AI systems. By leveraging the AI's ability to classify and predict phases of physical systems, scientists can explore and develop materials with specific, desirable properties much more efficiently. One of the most exciting applications is in the development of novel superconductors. Superconductors have the potential to revolutionize industries by allowing for the transmission of electricity without resistance. thus eliminating a significant amount of energy loss currently experienced in electrical grids. The AI technique can simulate and predict the conditions under which new superconducting materials might operate, speeding up the discovery process and potentially leading to more sustainable energy systems. Similarly, in the semiconductor industry, where the properties of materials at different phases directly influence the efficiency and capability of electronic devices, this AI can be used to predict new semiconductor materials with superior performance. This could lead to advancements in everything from computers and smartphones to solar panels and electric vehicles. Beyond superconductors and semiconductors, this technique also has applications in creating materials with specific optical, thermal, or mechanical properties. For instance, materials that can withstand extreme temperatures or pressures could be invaluable in aerospace applications, where materials are subjected to harsh conditions. By predicting how materials behave under such extreme conditions, AI not only aids in designing better materials, but also ensures safety and efficiency in their application. The breadth of potential applications underscores the transformative impact of this AI technique on material science. It opens up a realm of possibilities for innovation across various sectors, pushing the boundaries of what is possible in material design and application. To illustrate the practical impact of the generative AI technique in physics, let's look at several compelling case studies. These examples showcase how the technology has been applied to real-world problems, providing insights that were previously out of reach or would have required significantly more time and resources to uncover. One of the most significant achievements using this AI technique was in the field of superconductors. Scientists used the model to analyze patterns in known superconducting materials and predict which other compounds might exhibit similar properties under certain conditions. The AI successfully identified a new material with high-temperature superconducting properties that had been theoretically predicted but not yet synthesized. This breakthrough could lead to the development of more efficient power grids and transformative energy technologies. In another case, the AI was employed to accelerate the development of new photovoltaic materials used in solar panels. By simulating various compound combinations and their responses to different light spectra, the AI identified a novel material that offers greater efficiency and stability than current options. This discovery is pivotal for the solar energy industry, aiming to enhance the performance and reduce the cost of solar energy production. The AI also played a crucial role in the aerospace industry by predicting materials that can withstand extreme conditions, such as high radiation and temperature fluctuations in space. The technique was used to simulate and predict the behavior of composite materials under such conditions, leading to the development of a new composite with improved thermal resistance and mechanical strength. This material is now being used in the construction of spacecraft and satellites, enhancing their durability and performance. These case studies demonstrate not only the versatility of the generative AI technique, but also its ability to drive innovation and solve complex problems across multiple industries. By providing a faster, more accurate means of material prediction and classification, this AI is revolutionizing the way scientists approach material discovery and development. To provide a deeper insight into the revolutionary impacts of generative AI in physics and material science, we reached out to several leading experts in the field. Their perspectives shed light on the future directions of this technology and its potential to further transform industries. Dr. Cho, a pioneer in the application of AI in material science, emphasizes the transformative nature of this AI technique. The ability to predict and classify material phases using AI not only accelerates the discovery process, but also significantly reduces the costs associated with experimental methodologies, she explains. Dr. Cho highlights a project where her team used the AI to identify a new alloy that is now used in high-strength, lightweight automotive parts, showcasing the direct application of this technology in industry. Dr. Strauss, a physicist specializing in superconductors, discusses the implications of AI in understanding and creating new superconducting materials. What used to take years in terms of experimentation and data analysis can now be achieved in months. This AI is not just a tool, it's a game changer that pushes the boundaries of what's possible in physics, Dr. Strauss remarks. He foresees a future where AI not only aids in material discovery, but also helps in predicting physical phenomena that are not yet understood. In a recent panel discussion featuring leaders from various technology sectors, the consensus was clear. The integration of AI into material science and physics is paving the way for innovative solutions across industries, from renewable energy to electronics and aerospace. The panelists discussed several ongoing projects where AI-driven discoveries are leading to more sustainable and efficient technologies, highlighting the broad impact of these advancements. These expert insights confirm the critical role of generative AI in driving forward scientific discovery and industrial innovation. The enthusiasm and optimism shared by these leaders reflect a shared vision of a future profoundly shaped by AI-enabled technologies, where the possibilities seem almost limitless, challenges and limitations. While the advancements in generative AI for physics have opened numerous doors for innovation and discovery, it's important to discuss the inherent challenges and limitations that accompany this technology. Addressing these issues is crucial for realistic expectations and the responsible development of AI applications, data quality, and availability. One of the major challenges lies in the dependency on high-quality, extensive datasets for training the AI models. Dr. Emily Cho points out, the accuracy of our AI predictions is heavily dependent on the quality and variety of data it learns from. Poor or biased data can lead to inaccurate predictions, potentially setting back research rather than advancing it. Ensuring the integrity and breadth of data used in training these models is paramount to their success and applicability. The computational demand for running sophisticated AI models is another significant barrier. These systems require substantial computational power, which can be a limiting factor for some research institutions or smaller companies. Dr. Alan Strauss notes, the resource intensity of training and running these AI models means that access to cutting-edge discoveries can be uneven, potentially widening the gap between large and small players in the field. As with any powerful technology, ethical considerations must be addressed. The potential for misuse or unintended consequences of AI-driven discoveries in material science and physics raises important ethical questions. There is also the issue of job displacement in traditional roles, as AI begins to automate processes that were previously carried out by human researchers. Scalability and generalization. Lastly, the scalability of AI applications and their ability to generalize across different types of physical systems remain challenging. While AI can excel in environments it has been extensively trained in, its performance can falter when confronted with novel scenarios or data outside its training regime. This limitation underscores the need for ongoing research and adaptation of AI models to new challenges and datasets. Despite these challenges, the potential benefits of generative AI in physics and material science are undeniable. However, moving forward requires a balanced approach, addressing these limitations while continuing to innovate and explore the capabilities of AI in this exciting field. As we've explored the groundbreaking capabilities of generative AI in physics, it's clear that this technology is not just reshaping our understanding of material science, but is also poised to have profound social implications. By enabling the rapid development of new materials and technologies, AI has the potential to significantly impact various aspects of daily life, from energy consumption and environmental sustainability to healthcare and transportation. The democratization of technology, driven by AI's ability to solve complex problems more efficiently, promises to make cutting-edge technologies more accessible to a broader audience, potentially leveling the playing field between developed and developing regions. However, as we embrace these advancements, it's vital to consider the broader social impact, including ethical considerations and the need for equitable access to technology. The future of generative AI in physics and material science is incredibly promising, and as we continue to push the boundaries of what's possible, we must also ensure that these technologies benefit all of humanity. With that said, thank you for watching, and until next time, keep exploring the limitless possibilities that science and technology have to offer.